Welcome, everyone. My name is Marty McCann, and I am the chairman of the Committee on Geotechnical and Geologic Engineering. COGGE, as we refer to it, is a standing committee of the Board on Earth Sciences and Resources within the National Academies of Sciences, Engineering, and Medicine. The National Academies is a nonprofit organization. It's private. It's a non-government entity that was set up to provide independent advice to the government, founded originally by Abraham Lincoln. COGGE is the focal point within the academies for the exploration of geologic and geotechnical engineering research and practice issues to serve the government and the public. We're fortunate to have a number of core sponsors of COGGE. These include the National Science Foundation, NIOSH Office of Mine Safety and Health Research, and the Federal Highway Administration. And in particular, we're grateful for a grant from the National Science Foundation to help support these webinars that we put on a regular basis. This is the latest installment of our webinar series. We have been building out our webinar calendar now through 2021. So you can expect regular webinars over the coming months and years as we move forward. I'd like to make everyone aware of the fact that COGGE meets twice a year, and our upcoming fall meeting is October 1, and that meeting is open to the public, so you can register to attend that meeting. And as part of each meeting, we typically have a topical area that we're going to discuss and invite speakers and have a QA session. And this year, our subject is incorporating geoprofessional input into improved decision-making for infrastructure. If you're interested in participating, you can contact Sam Magsino, the Executive Director of COGGE, for the registration information, or go to our website. That meeting will have a series of speakers. The speakers then will serve on a panel, and people in the audience will be able to ask questions, and we'll also be having a number of polling questions during the course of the meeting that folks can respond to. So with that, I'd like to move to today's webinar. Our webinar is going to be moderated by Dr. Scott Anderson of BGC Engineering in Golden, Colorado. Scott is a member of COGGE. He has a long distinguished career, and in particular spent time at the Federal Highway Administration, where he was involved in research, teaching, and consulting on highway projects. Scott got his PhD at the University of California, Berkeley, and as I said, will be today's moderator. Scott will be aided by Professor Pedro Agrino from the University of Washington in providing questions to our speakers today. So with that, Scott, I'll turn it over to you.
Hey, welcome everyone. Thank you, Marty, for that introduction and getting us started there. I'm really excited to have this role here today to introduce this topic, which is quite important to me. When we think back about it, our profession is one that's grounded in getting data. We always had a sort of a reconnaissance step in our project development, but it was usually a low dollar kind of let's get it started thing. But we really got eager and got out to get drilling and collecting samples and testing them. And in fact, when I first joined the Federal Highway Administration, my first office was in the materials lab. And that's because we collected data. And that changed pretty quickly. And actually, one of my roles with the Federal Highway Administration, with others, was to go around to different state departments of transportations. And we basically helped a lot of them realize that the home for the geotechnical profession was not in the materials lab, but with the project development groups, whether it's structures or roadway or what have you. And that's because the geotechs had information, and that was valuable to the project development. And then, as time went on, there started to be this fear, like maybe we're too much in the information realm and we're losing the ability to collect data. I remember times where, there was concerns about whether we were collecting enough lab data and would continue to do so in the future. About the same time, states were, in the transportation sector, were starting to collect and recognize the importance of all the data they've collected, and they had GIS for their own individual use, and they're all sort of proprietary and had their own descriptions of things. And some, major consulting firms that I practiced with at the time had the same kind of things going on, and similarly, around that period of time, there were some people, I think overseas, first to the AGS, that was started thinking we need to standardize some of this. We need to get these data in a standard format. And that started maybe back in the 90s as well. And followed, although AGS continues, with an organization called DIGGS, and DIGGS, the Data Interchange for Geotechnical and Geoenvironmental Specialists. And this is a system whereby these different data sets could be made to communicate with one another by standardizing the way things are described and the data fields are organized. And there's a schema for that that's now published here in the US. In fact, tomorrow's a noteworthy day with respect to all that. Tomorrow, the AASHTO, the American Association of State Highway Transportation Officials, for those of you not in transportation, it is about to publish Provisional Practice Standard number 102, which will make DIGGS available for all state DOTs to reference, and it should help expand this nationally. The DIGGS idea is really important because it allows an owner to get a lot of efficiency out of their data. But from our perspective here today, what we're talking about is transforming. And what's transformative is that it's efficient not only because it's efficient at a given project level or at the agency level. Think of it as being efficient at the data type level. All data types, whether they're recorded in one place or another for a highway or for a dam, can all be collected together. And this is transformative because it will allow practices like artificial intelligence and machine learning to take hold for us. If we had time today, we'd have a speaker on DIGGS, but we don't. So you've heard about all you're going to hear about it from me here just now. And we do have a couple great speakers coming up, and one of them is Professor Ellen Rathje, and she'll be followed by Thomas Stanley, who works with colleagues at NASA. And NASA had a pretty good morning. They launched something towards a vehicle towards Mars this morning, but they also do a lot of important things in our realm, and that's what we're going to hear from later in this session. Ellen's going to talk about a platform which in some ways is like DIGGS for an agency. The platform she'll describe will allow anybody to get multiple uses out of their data by publishing it and making it available to others. And she'll get followed by Thomas, and he'll explain what you can accomplish using different sources of data. Thomas's talk recognizes that there are about 8 billion data collectors on the earth. Those are people, and they're individual or they're self-organized by their employers or other kinds of organizations, and they collect data. And owners and agencies are collecting data by running instruments through their pipes or along their rails or down their roads at greater and greater frequency. And the data density is expanding tremendously. And, above the ground, leaving the ground surface, we get up in the air, and we've got collections. Multiple places in the US now have multiple episodes of aerial LiDAR, for example, and other kinds of aerial imagery. And we can get even higher in the sky, and we have Earth observation satellites that are launched daily almost by governments and by private entities. And Thomas will talk about some of these. So with that kind of introduction to where we're going and how these two talks relate, let me introduce Professor Rathje. Ellen is the Janet S. Cockrell Chair in Engineering at the Department of Civil and Architectural and Environmental Engineering at the University of Texas at Austin. And she's a senior research scientist at the UT Bureau of Economic Geology. Her experiences in the areas of seismic site response analysis, engineering seismology, seismic slope stability, induced seismicity, and remote sensing. She's the principal investigator for DesignSafeCI.org, the cyber infrastructure for the National Science Foundation's Natural Hazard Research Engineering Research Infrastructure. Dr. Rathje received her PhD in civil engineering from the University of California at Berkeley in 1997. Ellen, it's all yours. Thanks.
All right, thanks, Scott. Let me get to a point. Let me see if I can share my video. Eric, I think you're gonna need to help me with that, but I will share my slides. Give me a second to share that. All right, we tested this earlier and it worked. I'm going to try something different. I'm just going to share my screen. Here we go. All right. Get my laser pointer. I'm ready to go. Scott, give me the thumbs up. You can see everything there?
Yes, I can.
All right, wonderful. So thank you for that introduction and those opening remarks. Welcome, everyone. You see my title here. You might think it's a bit presumptuous or even ambitious, what data publishing can do for us. But within this talk, I really want to propose a vision in which data publishing becomes ubiquitous throughout the research community, maybe even beyond the research community. And through that will facilitate and accelerate research in geotechnical engineering and beyond. Now, if we think about geotechnical engineering, and Scott mentioned this, we really have a rich history of the use of data. You know, we can think about the design methods that are based on data, whether it's the alpha parameter for skin friction in pile design or the cyclic resistance ratio for liquefaction analysis. All of these methods are rooted in data. We can look at soil parameter correlations. You know, how do we derive fines content or undrained shear strength from a cone test? So again, all of that's rooted in data, those relationships. And then for specific projects, we often entail or utilize field monitoring, whether it's inclinometer data, settlement data, so we can really understand what's going on. So in all of these cases, we were making a huge use of data to understand what's going on in the geotechnical realm. If we look a little bit closer at what we call the data life cycle, you know, we start off with that data collection. Sure, it could, whether it's in the lab, the field, and even numerical simulation. Remember, we can think of data as being generated by a numerical simulation. But once we collect that data, we need to analyze it. Our tools to analyze it have really grown in the decades. Maybe at one point we were using Excel. Well, even today I still use Excel, but you know, we're moving on to things like MATLAB, Python, geospatial tools as well, GIS. And as we continue then, we come up with some findings and we publish a paper if you're an academic or a report, for a design report or a project in consulting. And generally that's the end of the life cycle. However, perhaps a few years later, someone says, what about that data we collected at that excavation a few years ago? I want to take a look at that. Might help me on another project. Well, we can't find it, right? You probably have a drawer full of hard drives, portable hard drives with lots of data there, and you can't find it. If you can find it, you can't make sense of it. And the question remains, can this work be reproduced that was done with that data? Can we integrate those data with other data that we're collecting today? Think about if we had blow count data going back a whole century, what we could do with correlations, for instance. So really integrating data sets to create new knowledge is something we all should be striving for. So that leads us to how can we extend that data life cycle? And that next step, that last step, is the data curation and publishing. And I know when I hear the word curation, I think of a museum, and it kind of doesn't make sense. What does that mean with respect to data? And it really isn't that complicated. It really is just organization. And I will tell you, I do not have this many shoes and they are not organized that well, but my data are organized that well. But what does that mean when we're talking about data? You need to have meaning. You want things to be meaningful, whether the folder name, the file names. If you've got data in a file, you need to label the sensors. What are the names of the sensors? What are the units of the data? Where were those sensors located? And it's important to document the relationships of how that sensor is located here. How did I compute that? What process or workflow was used to put that data together? And it may be as simple as adding a README file that explains naming conventions, workflows, etc. All of these things are going to answer this question. How will someone understand these data without having to call or email me? And so whenever I'm publishing data, I'm going, what would someone want to know to be able to reuse this or recreate what I did? And that's simply helps the curation process along. Now, one way I'm trying to facilitate data publishing is through what Scott mentioned, which is DesignSafe, which is an NSF-funded cyber infrastructure for natural hazards engineering. And within DesignSafe, we have a data repository called the Data Depot. So I'm just going to give you an idea of how you can publish data in the Data Depot, really at the highest level. We've got all the details on the website. So here's an example of a published data set within the Data Depot. First thing you realize, it kind of looks like a journal paper. There's authors, there's keywords, there's an abstract. So this was a centrifuge experiment data set that was published by Scott Brandenburg at UCLA. And as you scroll down, you can see it well organized. Let me explain what the model looked like. Where's the information about the sensors? And then ultimately you get down to the data files, all in one place for download and reuse. Now, how do we get there? You know, our philosophy at DesignSafe is to provide you a flexible data model. So these are somewhat structured, but flexible enough that they can represent different types of research, different types of data, but always ensuring there's some specified minimum metadata that people then can make sense of it. And so, for instance, we only have 5 different data models. We have one related to experimental work, simulation data, hybrid simulation data, field research, and then if you can't fit into one of the first 4, you use the other project. So, and there you can organize things however you like. But with this flexibility, which really helps you, describe your research the way you want to describe it, with that flexibility comes responsibility, because we are putting a responsibility on you as the data owner to describe the data well and fully for data reuse. The other thing I want to focus on is, why should you publish data? How can you make your data count such that your research is reproducible and your data are reusable? This really is not just an altruistic, socialistic community thing of we want to move the geotechnical regime community forward, but you want to get some credit for this. This does take a bit more work than usual, so you should get some credit for that. So, there's kind of 3 steps that I always talk about making your data count. So first of all, formally publish your data sets in a data repository. DesignSafe is just one. It is domain specific to natural hazards, but there are data repositories that are more generic for any type of data, not natural hazards, not even engineering. So Zenodo, Dataverse, Figshare, Dryad, there's others. Any of those are possible. Your data, you want it to have a permanent DOI, a digital location, not just a URL on your website. And that's because it's a permanent location that it's easy to for search engines to find, and makes it truly a more permanent archive. And I like to suggest to my academic colleagues to list curated data sets on your CV, just like your papers. You know, today your paper citations generally have a DOI. They may not even have page numbers. A data set is similar. And then the last thing, which is really important throughout the community, is that when you use your own data or someone else's data, cite the data through this DOI in your reference list of your paper, using the DOI and the citation language. So here's just an example, you know, within a paper where we reference the data set that's in Design Safe, and this is what it looks like in the references section of the paper with the DOI, which if you click on that electronic link, it takes you right to the data set. Don't put the DOI in the acknowledgements. Don't put the DOI in the text of the paper. Put it in the reference list. And in fact, with Design Safe, we try and make it as easy as possible to know how to cite data. So if you hit that blue citation button, you get the details here, and you can just copy and paste this into your reference list, or hit the download button and you'll get it in one of the standard formats. So I want to talk a little bit about what I consider exemplars of published data. Some of these, you know, fulfill all three of those bullets. Some of them don't. One of the really meaningful data sets from the natural hazards and geotechnical earthquake engineering world is the New Zealand Geotechnical database, which came out of the 2011 Christchurch earthquake, where they realized because of all the ground failure, they wanted to share as much of the subsurface data as possible. And so they started with CPT data in Christchurch, tens of thousands of CPT data available electronically, and they expanded that to the entire country. So anyone can start downloading these data and using them. It doesn't have a DOI, at least that I know of yet, but the key here is making the data pervasively available, subsurface data. Another effort led by the USGS is their earthquake-induced ground failure inventories. And so they have, you can download GIS files, but they also have a web app, so you can look at some of the landslide inventories. They're mostly focused on landslide inventories. There's 39 landslide inventories going back about a century for people to potentially use. They want liquefaction inventories as well. But we haven't done as well as developing those. And so they're still on the lookout for adding those. And then the last one I want to mention is NGL, which many of you may be familiar with, Next Generation Liquefaction Project, which is trying to put together kind of concise and reviewed liquefaction data sets in the same way we've done for earthquake ground motions. And so here you see the NGL website where you can submit their data. And again, a useful tool that will make these data available to all, not just those in the know, part of this little club of people who do liquefaction. I'm going to come back to NGL because when you think about having a lot of data, the whole concept of downloading data, maybe emailing data to your colleagues starts to get a bit cumbersome. And that's why I want to mention one other part of Design Safe is the workspace, which facilitates data integration. We have lots of tools here. I'm not going to go through them all. You know, there's simulation data, there's visualization tools, there's simulation tools. But the key is these are all on the cloud. And when I say the cloud, that means they're running on servers on our side, at the Texas side of the internet, where the data in the data depot reside, and you can then do your data analysis and visualization in the cloud. We also have, these simulation codes, long list of them that have access to high performance computing resources. So if that's your interest, you might want to check it out. But I do want to stay focused on the data side And one of the things that we are seeing an explosion of use is Jupyter Notebooks. And these are electronic notebooks, typically written in Python, but you can also write them in R. And within Design Safe, we have a Jupyter Hub, which means that the Jupyter, again, rather than running Jupyter locally, we're running them on our side of the server, and you have access to the data depot files. So you can create an interactive data viewer. You can write scripts, because again, this is Python for data. You can do it for data processing. You can do AI. You can do machine learning. And then ultimately, you can publish them so that others can use them. This example of this is a notebook that is linked to the NGL database. So the NGL database is mirrored every day to the servers at Design Safe. And these notebooks work on our end in our Jupyter Hub and access that data. And here's just an example of, cone data and different ways that you may analyze them. But through all of this, we're accelerating data reuse. We're accelerating the adoption of approaches that you're proposing into practice, because you're making not only the data available, but the scripts that make use of that data available as well. So I would be remiss in a session that says something about big data and not mention a bit more about these buzzwords, AI or machine learning. I'm sure we've all heard the terms. If you try and boil it down to a phrase, you say that these are algorithms that learn without explicit programming, without having to say, here's the functional form for the regression, or these are the steps needed. And they're well suited to capture complex relationships, which may be difficult for us to see with our, because we're used to looking at 2, 3-dimensional data sets at most. If you're talking about n dimensions, how do you visualize that? But of course, that means to use these algorithms, you need enough data to sample the range of inputs, outputs, or the range of complex relationships. So again, now you start to see the need for bringing multiple data sets together so we can have enough data to fully explore using these algorithms. And we always need to keep in mind, do the results make physical sense? Can we embed some of the physics in there? I will say I have been a skeptic for these approaches for many years. Maybe I've drank the Kool-Aid now that I work with a supercomputing center, but I do think there's a lot of promise in these algorithms, but we always have to keep the physics in mind. And I like to end my discussions about AI and machine learning with this quote from Dave Womble at Oak Ridge National Lab, because a lot of people don't want AI and machine learning because they feel like, oh, you're just trying to replace me. And I will say, and he said, and I will say it again, AI won't replace the scientist, but scientists who use AI will eventually replace those who don't. So again, a little bit presumptuous there, but 10, 20 years down the road, that may in fact be the case. So I want to kind of circle back to my initial premise of the data lifecycle and thinking about how we can extend that data lifecycle so it goes beyond these 3 circles. Hopefully now we can change that data lifecycle and add a little circle at the end that you don't just publish the paper and report, you publish the data as well. And if many people are doing the same, those data can be integrated and analyzed into another finding. That data will be published in its own paper, or those results will be published in their own paper. Those data will be published again. And what you want to see is that this really becomes a web of data, of knowledge, of research findings that really pushes our community forward. So with that, I'm going to stop sharing and pass it back to Scott.
For that.
You're unmuted. Eric unmuted you, I believe, Scott.
Okay, thank you, Eric. Yeah, Ellen, thanks very much for that presentation. And that's excellent. Some ideas that I think probably some of our audience have some questions for. And I want to make sure to, if you haven't figured this out already, that there is a Q&A button. If you hover down near the bottom of your screen, I think it will show up. And it's a great way for you to start introducing some questions for Ellen. And we'll get back to those at the end of the talk, of Thomas's talk. And it's nothing that Ellen said, actually. I should have probably said this sooner, but I do want to remind everyone that all of the conclusions and recommendations that are presented here are those of the speakers, and they should not be thought of as representing the national academies or our committee, COGGE. So with that, I want to introduce our next speaker, Thomas Stanley. And Thomas graduated from the University of Maryland in 2014 with a master's in geospatial information sciences. And he joined the university's Space Research Association to develop static and dynamic models of landslide hazard at global and regional scales, in collaboration with other scientists at NASA's Goddard Space Flight Center. And these models rely on satellite-based estimates of precipitation, as well as remotely sensed observations and variables. And it's these kinds of data sources that Thomas will talk to us about and the application. When Thomas is done, we'll have questions and answers for both speakers. So Thomas, it's all yours. Thanks.
Okay. I'm just loading up the slideshow here. Okay, here we go. So I'm here to talk to you about the Global Landslide Nowcast, which we have running in nearly real time, covering the area between 60 degrees north and 60 degrees south. I work at University Space Research Association, but my office is actually at NASA Goddard Space Flight Center. Like a lot of people there, I'm a contractor who works with Dr. Delia Kirschbaum, who's the lead of the Landslides team there, as well as some of these other fine people that you can see on this slide. So the Global Landslide Nowcast, which is based around our Landslide Hazard Assessment for Situational Awareness Model, or LASA, produces a map of where landslides are most probable in nearly real time. It does take a few hours to compile all of the rainfall data after a satellite passes over, and so you are getting the latest possible information at the global scale, but it's not instantaneous. So we're typically looking at about a 4-hour latency from a satellite overpass to when the data actually is available to the public. Now, this model is fairly simple. You can see at top left the decision tree that we use to make these maps of hazardous terrain. And basically we say if the rainfall is high, and if the underlying susceptibility of the terrain to landslides is high, then we'll issue a nowcast. So if the susceptibility rating is very high, or the highest category, then we'll issue a high hazard nowcast. And if the susceptibility of the terrain is moderately high, then we'll issue a moderate hazard nowcast. And then if either the rainfall or the susceptibility is low, then we don't issue a nowcast. Now, as this implies, we're only trying to predict rainfall triggered landslides. We don't do, this model will tell you nothing about whether earthquakes can trigger landslides or whether human disturbances can trigger landslides or any of the other possible freeze-thaw, any of the other possible processes that can initiate landsliding. But it does tell you about a broad range of landslides that are potentially induced by rainfall. So in a moment, I'll tell you a little bit more about how we determine landslide susceptibility and what the rainfall data looks like. But I just wanted to note that we have the model running globally within NASA's, it's being run by NASA's Precipitation Processing Service. And you can find it on the web. Again, maybe the easiest place to look for it is at landslides.nasa.gov, but you can, it's actually, the actual data is at gpm.nasa.gov. And then the city of Rio in Brazil has actually developed its own version of LASA that just runs at the municipal scale. So it's a similar model, but they've made a number of changes to the system that greatly reduce the false alarm rate versus over what you would get if you just look at the global model. And I also wanted to mention that we have a a new version of the model coming out hopefully very soon. It has not been peer reviewed, but it does seem to be working pretty well. And we plan to be developing regional versions of that model for Southeast Asia and high mountain Asia as well. So this is what the global landslide susceptibility map looks like. It is produced from a variety of data sets, and we'll get into those in a moment. But you'll just see that at the global scale, it very much reflects the mountain belts. It looks very similar to a map of elevation. However, if you were to zoom in, you would find that actually the effect of some of the other variables is more pronounced at the local scale. And you can see that landslide susceptibility is highest along the chain of mountains that runs from the Alps all the way to the Pacific Ocean, but most prominently in the Himalayan range. And also there's quite a high susceptibility landslides all along the Ring of Fire throughout the Pacific Islands, the Philippines, Taiwan, Japan, and then around the west coast of the Americas. There are also pockets of higher susceptibility elsewhere, such as the east coast of Brazil, Central Africa, and elsewhere. So the way we made this global landslide susceptibility map is we combined these 5 variables: the presence of absence of roads, geologic rating, the distance to the nearest fault, the rate of forest loss, and the steepness of the slope. And we combined them all using a fuzzy overlay model, which is taking the ideas of fuzzy logic and simply assigning a fuzzy membership function to each of these variables based on a fairly comprehensive literature review. So this is actually a heuristic model. It's not a machine learning model, but it does produce a very it produces a continuous output and a very detailed 1 kilometer resolution output. So the other piece in the model, the other major input, is rainfall data, and we get that from a NASA product called iMerge. iMerge is actually the result not of a single satellite, although there is a global precipitation measurement mission core observatory that launched a few years ago. But iMerge actually merges the high quality data that you get from that core observatory with many other satellites into a single seamless product for the entire Earth. And what you can see here is a map of rainfall and snowfall for April 29th, 2020. And so this product gets updated every 30 minutes. And we actually don't take the 30-minute product, we take a daily aggregate, but the daily aggregates also get updated every 30 minutes. Due to computing limitations, we actually are only able to run the model every 3 hours currently, but it could be run every 30 minutes because that's how often the rainfall data sets are updated. So this is what the model output looks like. In kind of the faded colors, you can see Hurricane Willa moving up the Mexican coast. And this picture of the hurricane looks maybe a little different from what you're used to seeing because not a visual image of the clouds, but it's actually data that represents the intensity of rainfall within the hurricane. And you can see that there's also a long rain band stretching all the way up to Austin, Texas, in addition to the hurricane. I suspect that that is a related meteorological phenomenon, but it's apparently not all entirely the hurricane itself, which seems to be mostly intact over here. But you can see as the hurricane moves along, the resulting nowcast gets updated. So initially we see in this area near Toluca intense landslide nowcast, but it gradually disappears over time as the saturation of the soils decreases as the time goes by. It's also worth noting that nowhere in this animation is the eye wall of the hurricane on land. So you can have pretty significant impacts to a large area despite the fact that the hurricane has not actually made landfall yet. So you can't just look at where the eye of the hurricane is. You have to really look at the precipitation products to know where the hazard is. So that was a real-time application of the LASA model, but you can also take the LASA model and run it retrospectively. And if you do, you can generate a mean rate of nowcasting, which gives you some idea of what the hazard is at different times of year around the world. So here you can see the seasonality of landslides with a 1 kilometer resolution all around the world. And you can see that different areas have different different seasons in which landslides are particularly dangerous. While this is usually well known to the locals, this kind of visualization gives you a nice global view of where things are likely to be hazardous. And you can see that in summer, the landslide hazard peaks in the Himalayan area and then declines in the winter. And that's because of the strong monsoonal effects that you have in that region. And whereas other parts of the world, such as the coast of Brazil and the west coast of the United States, actually have almost an inverse landslide season to what you find in the Himalayas. Another potential application of this model is you can chain onto the end of it an exposure analysis. So taking some new data sets, the gridded population of the world, critical infrastructure from OpenStreetMap, and roads data from the Global Roads Inventory product, my colleague Robert Emberson has created maps that show where the potential exposure to landslides is the greatest. Now this is based off of the model. It's not based off of historically recorded landslides. So it doesn't tell you how many people have been impacted, but it tells you more where the most probable impacts will be. And so if you aggregate this by administrative district, you can then start to plan some policy recommendations as a result. So I just wanted to, since this talk is all about data, I wanted to mention that the data inputs and outputs of this model are not all the same size. And as you can see, we have the density of information we have for the meteorological variables, for the topography, and for the biological variable are much greater than the geological information that was available to me. Now, there are some additional geological data sets that are not included in this model, but I think that it's worth pointing out that I think there's some room for improvement. And so I would encourage all of you to get onto Ellen's platform or another platform and share the geotechnical information that you have, because we're really working with limited amounts of information when we try to do these global models. And just a brief word about the next generation of LASA. We'll actually be adding in some additional data sets, such as the snow mass and soil moisture from the SMAP Level 4 product, which is also put out by NASA. That product has a 3-day latency, but it's useful for understanding the antecedent conditions that exist before rainfall triggers a landslide. And these products are what are called data assimilated products, which means that they actually merge both observational data sets, such as satellite brightness temperatures, and models, that global circulation models that tell you where the rainfall is likely to occur, or how bright the sunshine is likely to be, etc. So we're still working on it. I would say, we're coming to the end of the process of revising the global landslide nowcast. However, I always welcome validation data sets. And as I mentioned, there are not a lot of landslide inventories that include dates and locations of rainfall-triggered landslides. And so if you happen to be sitting on one that has not been published already, feel free to contact me or let us know in some other way. And I'd also say that if you're a more casual participant and you don't have a huge inventory of landslides, but you just happen to see one, or you happen to read about one in the newspaper, I encourage you to join us. using our web application, Landslide Reporter, and it's designed to be fairly mobile friendly as well. So you can even do this from your phone. Don't stand in the middle of an active landslide to make a report, but you can observe from a safe distance and report it through this website, landslides.nasa.gov/reporter. So thank you very much, and I look forward to hearing your questions.
Thank you, Thomas. And thank you, Ellen, again. Now's a time for us to move into the questions and answers, and a good number of them have come in. If you have questions as we go through these, you can continue to submit them. It's probably the case that we're going to have more questions than we're going to have time to answer, and that's why we have Pedro here, who's going to help us stay on track and get as many of them answered as possible. So with that, Pedro, I'll pass it to you, and you can start with the questions.
Yeah, first, can you hear me? I hope that you can hear me. If not, please send a message. We have plenty of questions here, and I will try to connect some of those to see if we can get several of them answered at the same time. So, Ellen, some of the questions that I've been getting here, and maybe we can make them public later so that you see exactly how was the question, is about practitioners using the data. Is design safe? Is the hope that they are going to be using this data? Is the hope that they are going to be publishing their data? What about proprietary data? What is the motivation for them to put the data into design safe?
That is a great question, and it's one I think that we're struggling with because of the issues of the proprietary nature, and what is the incentive. Now, I will say as an example, the New Zealand Geotechnical database requires practitioners to put data in order to take data out. So if you have kind of this very specific application where everybody is contributing, but everyone is benefiting, that is one motivation. Design Safe is not under that same, very specific one type of application, but that's one example. The other, it's hard to say, I know a lot of companies like to keep that, they feel like that's theirs and that gives them the edge. And I don't know if we'll ever be able to overcome that unless everybody is sharing data. One last point is if it's data that you think it's not characterization data, maybe it's about a project where you think someone ultimately could use it to validate numerical models down the road. I think that like publishing a case history paper, publishing the case history data with it contributes to the whole research community going forward, and the entire community going forward.
Good. So you are indicating that you are making efforts, Design Safe is making efforts to try to attract the practicing community.
And I should make note, because I saw one of the questions, you can download data from Design Safe without having an account. You can, to contribute or to publish, you do need an account, but the account's free. So it's really open to the global natural hazards community. So I want to make sure that was clear.
So I will ask you another question, and then I have one for Thomas. But tell us, do you connect Design Safe and the infrastructure and the data model, the data set with other data sets like about for example, Zenodo, Dataverse, Figshare, Dryad, and non-hazard related data storage and curation? So other type of data curations that may be related to hazard, or maybe it's not related, like weather, for example. Are you making efforts?
They're not directly related now, but that's one of our goals over the next few years, is look at what are the places where this interoperability makes sense. Usually it means, do they have an API that we can tap, things like that. So that's something that is in our future roadmap, but it doesn't happen today. But I will point out that if you have a killer app, a killer idea like that would require this, talk to me, send me an email, because we're looking for those type of things. We don't want to kind of just build stuff because we think people need it. If we know a specific application where people need it, we have a lot more incentive to make it happen.
So I will be back maybe if we have time, maybe a couple of more questions for you, Ellen. But now, Thomas, have you been looking at the data, at the design safe data, this kind of very geotechnical data as part of NASA's possibility to use this data, or is not in your radar yet?
I really haven't dug through design safe very thoroughly. I've really just glanced at it. I would appreciate it if Ellen or anybody else wants to point me to global data sets or even major regional data sets. I have to say, I cannot incorporate like a local data set, even if it's typically, if it's very high quality, even if it's like at the municipal level or even the state level. It's too much work for me personally to aggregate those individual data sets. However, if somebody else were to do a meta-analysis of all of the unconfined compressive strength tests that are in design safe and put them into like a single global data set that was very organized and documented and convenient to use, then I would certainly be very happy to take a look at it. And if you have already done such a thing, just send me an email and let me know that your product is out there. I'm always looking for information like that, but it has to be, with the exception of landslide inventories, where I'll take just about anything I can get. Kind of the explanatory variables, they need to be relatively consistent at a global scale.
So Tom, related to that, there were a couple of questions here. One is, how was the criteria that you use for the validation of the data, that global data that you are going to use? And the second part is, do you have an available kind of API or some infrastructure that people can use to access the data and download it?
Yes, actually, we actually have two different APIs that people can use to access the Global Landslide Nowcast. One of them is can be seen at gpm.nasa.gov /precip. That's PRECIP-APPS, precip apps, and there you can find one form of API to pull the Global Landslide Nowcast. And then we also have a Esri REST API where it is made available at, and you can find that at landslides.nasa.gov/viewer. So that's our web app called Landslide Viewer. The data is also downloadable, so you can just download it, and if you don't feel like using an API. So those are all options. And I would note that in addition to the Global Landslide Nowcast, you can download the Global Susceptibility Map, and you can download the Global Landslide Catalog. So what is this Global Landslide Catalog? It's one of the many landslide inventories that have been published. It's the one that we use at Goddard, and that is our main tool for validating how well this Global Landslide Nowcast works. And to do that, we generally use a fairly standard presence or absence of landslides as a metric. So if we calculate a false alarm rate on the assumption that everything that isn't historically shown as a landslide is not a landslide, and then we can calculate a true positive rate or probability of detection based on the landslide inventories that we already have, particularly the Global Landslide Catalog. And so if you have both of those metrics, you can also calculate another metric called the receiver operating characteristic, and so you can get a sense of how well your model performs independently of a specific threshold as well. So if you read my paper on the Global Landslide Susceptibility Map, you can see the AUC value for that, not just for the Global Landslide Catalog, but for a few other landslide inventories that we were able to obtain. And in addition, if you read our paper on the Global Landslide Nowcast, you can see the true positive rate using different assumptions, as well as the false alarm rate, false positive rate for that Global Landslide Nowcast as well.
Thank you, Tom. Kind of related to that for Ellen now. Ellen, I will try to combine two questions that are kind of different, but maybe you can answer both. One is related to the previous one. Is there a review system in place to investigate the quality of the data? What is the standard structure? And you talk a little bit about the standard structure, but maybe you can use, that's one question. And the other question is related to where we are in our undergraduate and graduate education to push students to do this, and where we are in journals to start accepting these DOIs.
Oh my gosh, I think that's 3 questions, Pedro. And I
have like 25 here related to
Let me first tackle the quality question, because it's an important question, and it's a difficult question, because we all know how much time it takes to review a paper. And if you were given the assignment to review someone's data for quality, I would argue it could take 10 times as long as what it takes in a paper. So we do not have a formal review system, but we do have some mechanisms, or we're starting to initiate some mechanisms in place so that we can improve the quality. So for instance, a feedback mechanism where if you find a problem or an issue, you can flag this feedback and it'll get back to the authors so they can address it. So that it's kind of always a continuously updating process. Ultimately, the proof is in the pudding. You know, good data will be used a lot, and less, you know, the lower quality data may be used less. So that's kind of what we're hoping will ultimately happen. I'm going to hit the journals before I hit the education. I think something that's really exciting is that journals are now requiring you to make some sort of data statement. Either this is where the data is located, or this is why I can't share the data. And I remember, you know, not too long ago, if I tried to cite data with a DOI in a paper, ASCE changed it and put it back to a URL, and which was screwed up because ultimately that link broke. So they're coming along, and I think the journals realize the data sets are getting so big that they don't want to host these huge data sets as electronic supplements. And so that's exciting to see that they're promoting that. And the last thing is education. I think we want our students to feel more comfortable with computing. Does that mean I need specialized classes in geotechnical computing? Not necessarily. I do think every undergraduate should go through a computing class. I, for the first time, used Jupyter and Python in the class I teach, which is a sophomore class. But more importantly than that is that each class has to build on that. And I will acknowledge at Texas, we don't do a good job where you learn Python or MATLAB, and then in your structural analysis class, you use it. In your geotech class, you use it. In your hydraulics class, you use it. In our department, we just started a new degree program in environmental engineering, and they decided they were going to try and pervasively make this computation in the classes from the freshman year. So I think that's the way to make students more comfortable. We should see a little bit in all of our classes.
Okay, look, we have 2 minutes to go. 2 minutes to go. You will have 30 seconds each. Okay. The question is, data seems to be a case-by-case entry in the systems you are describing. What do you see as the future for innovation in pulling off this data with additional sources of data for additional data analytics and applications? Give me the innovations. 30 seconds. Tom.
Well, I think we need people to generate nice, comprehensive, authoritative data sets that amalgamate all of the smaller case-by-case data sets that are out there. That's my 30-second answer.
Good.
And I'll take the easy way out and agree, because that's what, you know, that will allow us to take advantage of things like machine learning and AI. If these cleaned up data sets that people all agree on the quality, then you can start doing the interesting things in the different algorithms.
Thank you very much, both of you. Tom, Scott, it's yours.
Thank you, Pedro. And I want to thank all of you in attendance for the great questions that did come in, and sorry we can't get to all of them. I want to thank our speakers, Thomas and Ellen, for some excellent talks that were really quite diverse and introducing you know, all the opportunities that are out there with data in our future. And as we saw through the Q&A period, these opportunities don't come without some challenges. So since challenges are what we all like, we're going to be having a happy time in the future, moving into a new realm of data use in geotechnical engineering. With that, I want to remind everyone that that the opinions that were shared here today are those of the speakers and not of the academies or of the committee, and to remind folks that there will be a recording of this session available in the future. If you have any ideas on things you'd like to see covered in the future, you can do so by reaching out to Sam Magsino at the COGGE website. Thank you all very much.